welcome to this new tutorial of OpenFOAM. Today we're gonna simulate a gas solid fluidized bed using OpenFOAM. So the material is available in this website. I'll copy this website in the description box. So you can download the simulation setup files and also the tutorial file. So this is our case. For the tutorial file, here it is, we're gonna work on it. So I have already downloaded the files of this test case, and we will go step by step using this tutorial. So here we have the license agreement. If you want to use this work or redistribute it or modify it, adapt it, you need to respect this license. So let's start now with our case. So for the test case, you can either download it from this link, simulation setup files, or it's already available in Foam Tutorials Multi-Phase, twoPhaseEulerFoam, RAS, Fluidized Bed, to copy it, for example, to home.desktop/desktop Fluidized Bed. So you have two choices to copy or to have this test case. Now, this is description of twoPhaseEulerFoam. So it is a solver of two non-reacting compressible fluid phase. So one phase is always dispersed, like particles or air bubbles, so we have always one phase which is dispersed and the other phase which is continuous. So this is very suitable to simulate a bubble column, for example, in gas liquid system or fluidized beds when we have solid particles dispersed in air. So this solver also solves the energy equation, so we can also get the enthalpy or internal energy, temperature as well. So it includes the energy equation for both phases, for the dispersed and continuous phase, and couple them by the one film resistance heat transfer model. So the case of gas liquid system, laminar and turbulence model can be selected for both phases, so we can specify either for dispersed or continuous phases. So for the gas solid systems, we have two approaches to model the turbulence, to include the turbulence effects. You can go to the user guide or the coding of OpenFOAM to check these two approaches. And also we have various submodels of drag and heat transfer and a lot of models that we will see in the files in the constant folder. So this is the definition of the problem. We have a fluidized bed. This is the dimension of this fluidized bed. So filled with up to 40 centimeter. We have 40 centimeter is already filled with 275 micrometer of spherical glass beds of density 2,500 kilogram per cubic meter. So for the packing fraction is equal to 0.6, and for the maximum packing fraction assumed to be 0.63. So these are physical parameters chosen for this specific case. For example, if you have another case, another solid with different density, you just need to substitute this value with your corresponding value. And also the geometry, you can modify the dimensions. For the packing fraction, also if you have different value or different maximum value of packing fraction, just go and modify this value. So the particles are fluidized with air at ambient conditions. So we have 1 atmosphere in pressure and 283 Kelvin. So for the other operating conditions, we will find it in table 1. So let's go and see the table 1. We have here the mean diameter, the density, heat capacity, the maximum packing, restitution coefficient, packed bed height, packed bed fraction, particle wall specularity coefficient, air viscosity, air density, air heat capacity, air prime number, superficial gas velocity, and the inlet air temperature. So just to have an idea about the parameters that you will need if you want to set up a fluidized bed case. So when defining the physical parameters of your case, so let's now go to the simulation setup. Here we'll define phases and interface coupling parameters. So it's defined in constant phase properties. So here is our test case and constant phase properties. So in this file, we have the defined phases. We have particles, which represent the solid particles, and the continuous phase, which is air. So for the particles, we are defining here the diameter model, it's constant. And the mean particle diameter is equal to 2075 micrometer. So here is the packing fraction, the maximum value, which is 0.63. And for the air, here because we have a continuous phase, so the diameter is specified usually equal to 1. So let's go return to the tutorial. Here, yes, we already saw this. And sigma virtual max. So yes, so let's return to the file. Here we have the blending. It's not type noun, so we don't have blending. Sigma, it's the surface tension between particles and air is equal to 0. We don't have any tension. And for the drag model chosen for the particles in air is JDASPO Ergon 1U model. You can choose your model. There are plenty of models in OpenFOAM. Just check the user guide or the code of OpenFOAM and you will see the available models of drag. You can also add your own drag model. For the virtual mass, we don't have it. And for the heat transfer, we choose this model for particles in air. And the lift, we don't have it. Warm lubrication, turbulent dispersion, all these parameters, all this model, sorry, we don't mention it because it doesn't have a really higher impact in our simulation. So if you have, for example, if you have a case where you assume that the lift particles in air is high, you just need to go here and define the parameters of your model for this part. So here we have phases and phase definition. Phases, particle subdirectory, alpha max, isothermal, list of diameter model. So this is for the documentation. If you want to see, for example, here, diameter model is here chosen constant. If you are interested in other models, you can find that here. So we have isothermal model, IATE models, and so on. So you can choose the models according to your need. The same for interface drag and heat transfer. So here, as I said, we choose the JDASPO model for the drag and Rance Marshall for heat transfer. For more details, you just go here in this tutorial and look for the available models. For example, here the drag models available already implemented in OpenFOAM. So for the turbulence now, we will go and check the file of turbulence. So we have two files in twoPhaseEulerFoam. We have two files for the turbulence properties, one for the continuous phase, which is air, and the other one for the dispersed phase, which is the solid particles. So we will check this one. For the turbulence properties of air, we are choosing RAS simulation type. So it's RAS. We can delete these lines because we are not working with LES. So RAS model, choosing K epsilon, and we activate the printing of turbulence parameters and also the coefficients of turbulence. And here we have the turbulence properties of particles. So here also we choose the turbulent simulation RAS, and for the model we are choosing here kinetic theory. We are printing turbulence and also its coefficient, and here we have the different parameters of this model chosen for the chosen to model the turbulence of particles. So here in the tutorial, so this is our file. So the model kinetic theory selected here. The viscosity and hence the shear stress tensor of the solid phase is estimated by a property called granular temperature. So here we are introducing a new parameter, which is granular temperature. So two main options are available for estimating granular temperature: algebraic relations and transport equation granular temperature. So here you can set the equilibrium. So these parameters explained here, it corresponds to the parameters here, equilibrium and other parameters. So if you are interested in this model, at first you need to go and look for the reference of kinetic theory model written already, and then check its implementation in OpenFOAM. And also you can read this information mentioned here in this tutorial. It may be helpful for your case to understand how does it work. So we have other models for solid phase properties, for viscosity, conductivity, radial function models, frictional stress models, granular pressure models. So we have plenty of models implemented in OpenFOAM, and you can choose according to your case, according to what you need to do in your fluidized bed. So for turbulence properties of air, we already saw this. In addition, so we have these are the available turbulence models in twoPhaseEulerFoam for the continuous phase. So now for the physical properties of phases, we have it's defined separately in the thermophysical properties .air and .particles. So here in constant folder, you will see that we have thermophysical properties of air and thermophysical properties of particle. So the properties of air are described. You can select the type of physical model of the phase thermotype. Let's go and check in thermophysical properties of air. So here the type is HE rho thermo. That means that the properties are calculated based on the enthalpy and internal energy and also the density of the mixture. And finally, entry energy. Let's check. Here we have sensible internal energy. Two options are available. You can choose either sensible internal energy or sensible enthalpy. The first option, which is sensible internal energy, tells the solver to solve energy equation based on the sensible internal energy of the phase, and the second, it solves the energy equation based on the sensible enthalpy. So for the other thermophysical properties of particles, the other phase. So here is this file. So here we have constant density assumed to be 2,500 kilogram cubic meter. So here we have rho equal to 2,500. Then the dynamic viscosity is set to 0. The stress tensor calculated from KTGF. And here we have the effective conductivity for enthalpy equation, kappa. Laminar part is calculated from the values you supply in this file, calculated as mu per print. So here you can check all these parameters. The print number is equal to 1. Dynamic viscosity is set to 0. Here for the thermodynamics, here the capacity, the heat capacity, you can check it in the table we showed before, the physical parameters in the table. So here the heat capacity, and the enthalpy of formation is equal to 0. And for this species, we have mole weight of 100. And for the thermotype is chosen the same as in thermophysical properties of air. And also in the constant folder, we have the gravitational file, which is G. So here we have equal to minus 9.81 in the y direction. So for now, generating the geometry in the mesh, we have the block mesh in system, here block mesh dict. So we have the vertices here that define the dimensions x, y, and z of the fluidized bed. And here we have the partition of each block by simple gradient. So to generate the mesh, we'll go in the test case, we will open in terminal, then we will type block mesh. So we have the mesh already generated. Perform to visualize it, apply, and here we have our geometry. So we have here our mesh. I'll color it using solid color. So this is our mesh in the X and Y and Z direction. Now for the boundary and initial conditions, it's in the 0 folder. So here we have all the boundary conditions that should be filled before running the solver twoPhaseEulerFoam. We have here the velocity, we have here theta particle, we have here temperature, here pressure, we have the viscosity, K and epsilon for turbulence, also here in alpha T for air and particles, and alpha dot air and dot particle, which corresponds to the volume fraction of the phases air and particle. So let's start here with the velocity of air. So we will see the command here. The boundary conditions of the air velocity are specified for all the walls. Non-slip condition is applied, and here for the inlet we have interstitial inlet velocity is applied. So in gas fluidized bed, superficial gas velocity is known, which is the average velocity of gas when the bed is empty. So this is the superficial gas velocity. So it corresponds to the average velocity of gas when the bed is empty. So here we have both air and particles in the inlet port, and the void fraction of these phases changes during time, because we are like injecting the air from the bottom, then the particles are more and more dispersed, and the void fraction, it changes during time. So with fixed value boundary condition for the air, constant superficial gas flow in the inlet won't be achieved. So because we have that void fraction that changes during time, each time we will have a velocity different in the inlet. So we cannot apply a fixed value in the inlet, because otherwise the simulation will crash and we will not be able to identify the error. So the error is this: when you apply fixed value and you have the void fraction that changes, so the velocity in the inlet changes, you need to assign different boundary type, which is interstitial inlet velocity. In the outlet, it will be assigned pressure inlet outlet velocity. So this boundary type, it's chosen when when the outlet velocity depends on the inlet velocity. So here we are defining this boundary for the inlet, and the outlet will depend on the pressure in the inlet. So for the inlet, we are choosing this boundary type, and for the outlet, we are choosing this type because it will depend on the pressure applied in the inlet. Hope it's clear. So for the particles, we have velocity fields. For the velocity fields is specified. So for the velocity of particles, the boundary conditions defined for these parameters are in this file. So here we are choosing the inlet fixed value, since we have here the particles don't cross the inlet and outlet ports. So for example, in the air, for the air phase, we have introduction of air from the inlet and we have evacuation of air from the outlet. So we have that movement, we have that flow. So we are specifying velocity, but for particles, we don't have input of particles from the inlet or output from the outlet. So particles do not cross the inlet and outlet ports. So the velocity of particle phase is set to 0. It's specified fixed value, uniform equal to 0. So for the walls, we are setting up this model, Johnson-Jackson particle slip, because we don't have neither slip the particles in the wall. We have here granular flow, and in granular flow, usually the particles don't stick to the walls. We don't have solid particles that stick to the wall, and also we don't have that kind of particles that don't slide freely, on the wall. So both particles don't stick to the walls and also don't slide freely in the wall following the slip conditions. So this is why we are choosing this model. This is the formulation of the implemented model in OpenFOAM. You can check the theoretical base of this model and also its implementation if you are interested in. And also we have 0 theta dot particles. It corresponds to the granular temperature. So here we have reference level, which is 10-4. Is specified, is initially added to the value of the field in the cells and boundary patches for time 0. So in this way, the value of theta will be non-zero in the cells and boundary condition and will prevent invalid math operations. So we are imposing, applying this value in order to avoid invalid math operation on granular temperature like division by 0, which may cause the divergence of the simulation. And here for the scalar field for temperature, here we have temperature of air and particles. We have 0 gradient, 0 gradient. Anyway, it's constant in all the boundaries, so I don't think we will have heat transfer in the in this case. So we have 0 gradients, 0 gradient in the inlets and inlet outlets. So the outlet will be impacted by the temperature in the inlets, and all the values of temperature assigned are equal to 288. So I think it will be 288 in the when finishing the simulation. Here also for the turbulence, we are specifying for the wall function at the wall, which is K, Q, R wall functions for K and epsilon wall function for epsilon and not K wall functions. So these are wall functions for turbulence in the wall. So we can check here epsilon. So here we have for air we have function in the wall, K also, and epsilon. So here to initialize the packed bed of particles, let's see at first alpha air and alpha particles. So here we have 0 gradient at the inlet, 0 in the outlet, and walls also 0 gradient. And also for alpha air, it's the same. So we don't have neither air or particles at time equal to 0. So what we need to do is to go and set, as you can see here, we need to have solid particles up to 40 centimeter height with packing density. So here we have, and hence the upper part of bed is empty. So we will have the part near the inlet will be set with solid particles up to 40 centimeter. Then the upper part will be empty with alpha air equal to 1. So for this, we'll go to System folder, Set Fields, and here we are creating our box, and we are assigning the height of 40 centimeter, which is 0.4 meter. And we are specifying that in this box, we have alpha air equal to 0.4, which is 40%, and the alpha, the solid volume fraction of particles are equal to 60%, which is 0.6. Here specified here, packing density of 0.6. So now what we need to do is to run the set fields in order to get these values. So we will do set fields. So here we have, we are packing particles and air in the geometry I'll run perform to check. Apply. And alpha particles. So here you can see that we have I'll show the grid. So yes, it's 0.4. So here we have 0.6 of alpha particle equal to 0.6 in this part, and in the other part it's equal to 0. So here we have air. In this part we have 0.6 of particles and 0.4 of air. Then for running the simulation, we already run this command block mesh for generating the mesh, set fields for packing the solids in the bottom, and then here twoPhaseEulerFoam to run this simulation. So I'll close ParaView and I'll run the simulation. twoPhaseEulerFoam. So after running the simulation, it really takes a while. So I stopped my simulation here at the time of 3.17. For the control dict, it's assigned until the end time is 5. I modified the right interval. It was 0.01, so I make it 0.5 in order to get less folders. So for the first folders, I have a recording frequency of 0.01, but after 0.5, I changed the frequency of writing the interval to 0.5. So here I have my results. So I'll run the ParaView in order to show you the results of our simulation of Fluidized Bed. Apply. I color it with alpha particle. I'll change the color, jets, apply. And here we have, I'll annotate time, apply. So this is for time equal to 0. Then here you can see the evolution of alpha particle with time. So here we have a time equal to 0.5 second. So here we have the results in the tutorial. So this is in 0.5 seconds. So this is the screenshot. So approximately it's the same. So we have alpha particle here. Then we gonna rescale it. So it's rescaled like here in the tutorial from 0 to 0.63. So we can make a comparison of our results. So here we have for the time equal to 0.5. So this is 0.5 second here. and for the time equal to 2 seconds. So time equal to 2 seconds. And for this time, I stopped the simulation at the time 3.17, so I don't have the final screenshot at 5 seconds. You can push your simulation to get to this time and see what does it give. So this is the simulation of Fluidized Bed. You can make your animation by going here, save animation, name it A animation. Okay, then we'll change to white background, then okay, so okay, and we will wait until it's done. So I think our animation is ready now. It's recorded here. So it's very slow in the beginning because we have small intervals of 0.1. So you can see the evolution of the bed, the particles bed here. So this is the animation. Okay, so this is all for this tutorial. Thank you for watching, and if you have another tutorial like this one, don't hesitate to copy the link in the comments in order to get a video on it like this one. Thank you again for watching, and see you in next video.